today I would like to review how to do two-dimensional momentum. Let's pretend you have a pool table. Oh, we're looking down to the top. That looks like a top. Yeah. If we have, say, the cue ball is going toward the 8 ball. And it's going to hit it at some angle. Then the 8 ball is going to go off that way. And the cue ball is going to go off that way. And what you're going to find is that if the masses are the same, like they are here, you will always form exactly a 90-degree angle between them. Which is helpful to know when you're playing pool. Because sometimes you focus on where the ball you're shooting is going to go in, but you're not paying attention to what's going to happen to the cue ball.
Oh, that's true.
Yeah, and then it goes in the pocket that you weren't expecting, and you say, oh, right. So, before the collision, all the momentum was in the cue ball.
Yeah.
And then afterwards, we have both of these. So we know the total momentum before should equal the total momentum afterwards. So if we take the 8 ball afterwards, and we head to tail it with the cue ball afterwards, that should equal what the cue ball was before.
Yep.
And again, what's conserved is momentum, so these all have to be momentum numbers. So momentum, of course, or just P equals M being it. But what's going to happen is, again, this angle will be how far over did that go, and this angle is actually how far over did this go, because when you move it and you work out the geometry of it, it comes out to the same angle over there. So this is how much the 8 ball was deflected to the left, and this is how much the cue ball was deflected to the right. So for both of them, really, since this is the 90-degree angle, that means the original momentum is the hypotenuse, and you're always looking for the adjacent side. So if you just take the cosine of the angle, and normally you would multiply it times the original momentum, that's going to equal the momentum afterwards. But again, since P equals MV, you're really going to have cosine of the angle times MV equals MV after. But we said that these M's are the same M, so they would cancel out. And it would work the same thing for the 8 ball, because for the 8 ball, it also has the same mass. So really all we have to take is the cosine of the angle times its initial velocity, and that would tell us what the speed is going to be afterwards. So that works out super duper simple if the masses are the same. And they are in pool. But lots and lots and lots and lots of other things, they are not the same. So what happens when they are not the same? And we just give up and we cry and we throw in the towel.
Just not fair.
We say, it's not fair, man. Why can't life just be simple?
Right? Don't you just wish there really was an easy button?
There is.
Here it is. Stop it.
It always asks you, when you start, it asks you, easier or harder?
Yes. How many of you have ever worked out with weights before? Why would you work out with weights?
Because they're weights.
Because if you push your body harder, it gets, yeah. And if you run, the first time you go running, you huff and puff and die. But if you keep running and keep pushing, what happens is you get
Get used to it.
better, and there's less huffing and puffing. And okay, for some of you, you have to like do it on a regular basis. Same thing works with your brains. We try and actually push our brains and not use the easy button. It becomes easy because we familiarize ourselves with it. I keep trying to convince people that if you actually do the homework, you're actually practicing for the test. But people keep like, nah. Why would I want to do that? Okay. There's a boat. Not a very aerodynamic looking boat. Okay, here's a boat. We're looking down from the top. Here's its little weight coming through the line. It's a boat!
It's a torpedo.
Boat!
Ball construction.
Gonna see.
You're looking down from the top.
Gonna see it has a few holes in it.
That's a boat, and it's floating by, and there's this
Iceberg.
round thing that's floating in the water in front of it. A buoy. Okay, so the boat is 242 kilograms and is traveling at 12.3 meters. That's fast.
Yeah.
2.49 meters per second.
100.
Okay. That was gonna be really fast. So, and it's coming along toward this buoy who has a mass of 146 kilograms.
Yeah, boy.
Now, judging by the angle that this is traveling and where it's going to hit it, what's going to happen?
Maybe it's elastic. You saw the text.
This is going to go that way afterwards. It's not up. We're looking down from the top. It goes to the left. Because if this comes along and hits it like that, it's not hitting in the middle. Do you need level to see that? There we go, see? Okay, so it's going to go to the left, and so the boat's going to get deflected not at a 90-degree angle. Why is the boat not going to be at a 90-degree angle?
Who's heavier?
Because the masses are not the same this time. Ooh.
Oh, that means we have to cry.
Okay, so what we need to do then is we need to know is what angle is one of them deflected and how fast is it going afterwards. Okay? So if we say this gets deflected 32 degrees to the left, and it is now traveling at 2.17 meters per second, we want to know how fast the boat is going and at what angle was the boat deflected in this collision. Everybody understand?
Yes.
Okay, now the only thing that can go on these, what is it that gets conserved in a collision?
Momentum.
Yes, momentum is the only thing that gets conserved in the collision. So the only numbers that we can figure out are momentum numbers. So first we gotta say, before they collided, all the momentum was in the boat. So that was delayed reaction. So P equals
Super weird.
super delayed here.
Magic.
So the total momentum we had before the collision
2.58.
So we have 602.58 Newton seconds of momentum before they collide. Correct?
Yes.
Now, how much momentum does this buoy have after it collides? We're going to say 146 times 2.17. So now it's going to have 316.82 Newton seconds. Going that way. Now, if we have an angle, we can say, hey, some of this momentum is going forward and some of this momentum is going to the side. The forward part is the which side of the triangle? Adjacent. So I would want to use cosine. So if I take cosine 32 times 316.82. At some point I'm going to start rounding here. So we have 269 Newton seconds of that is still going forward, and we would use sine for the other side where we would have 168 Newton seconds going to the side. Everybody with me so far? So here I took the cosine of 32 times 316 and got to 269. Here I took the sine because it's opposite. So it's just cosine sine. You totally know how to do that, right? Alright, so now the boat, you say the boat is also going forward and to the side. And we can figure out how much is going forward and to the side because we know that in a collision, momentum is always conserved. So before the collision, we had this much going forward. How much do we have going forward now? How much is missing? You subtract them. So if I take the 603 minus the 269, there is 334 Newton seconds missing. So there must be 334 Newton seconds going forward in the boat. Now, before they collided, how much was going to the left or the right? Say 0. 0. Hey! Somebody did say 0.
I did. I said 0.
Oh, so they have to cancel
out.
It was Nick. He said 0. Hey, Nick. Okay, so how much should there be after the collision? 0. So if we got 168 going left, we must have
168 going right.
168 going right.
It's like cheating.
It's like cheating. It's so easy.
Cheater beater.
Okay, so if I know this one and I'm looking for the big side, I would like to Pythagorean. So 334 plus 168. I got 374.
Yeah.
So I got 374 Newton seconds. Now, if I want to know how fast the boat is traveling, the numbers that are on the triangle are all what kind of numbers? Momentum numbers. So again, P equals MV. So if I'm looking for V, the M needs to come down. So we're going to have the 374, and we're going to divide it by what M?
The boat.
The boat mass, which is
Although when it collided, it lost mass, right?
yes, it lost speed.
Are you sure?
Yeah, what if you like
That's
cut
What
a
if
chunk?
someone fell off the boat while they're like,
Yeah, that's true.
Yeah, take that into
Take that
account.
into consideration.
Also. What if I fell off? What if I punch you in the face?
do it!
Then I get a mark.
And the suffering!
You're going to provide an impulse that changes the momentum of your head.
Well, we gotta figure out how far back, so
Yeah.
do a test.
Let's try He's gonna listen to these videos and then finally get sued.
Oh, you're recording? Are you recording right now? Hi! How did you treat me? Because I'm probably gonna have to watch this video again, so.
Okay.
Guess I wasn't paying attention now. Okay, so the only thing we haven't figured out is the angle it got deflected at. And how do we find the angle? Inverse tangent. So tangent minus 1. And what always goes on top?
Opposite.
Opposite, which is
168.
over adjacent, which is
334.
Oh yeah. Wait, is it 334? Oh yeah. Oh yes.
so you get 27 degrees to the right. So if you add up your two angles,
No way. No way. I add them to 90.
it does not add up to 90. Why do they not add up to 90?
Because they did something wrong.
Because they have different masses.
Oh yeah, that's true.
If they have the same mass,
Inelastic.
they go off at 90. These have different masses, so they don't add up to 90.
So always end up to 59.
No, they don't always end up to 59.
It's only 98.
So is it negative 59?
Person.
Okay, you should know enough now to be able to solve.
Remember that the Titanic went negative.
Yeah. But like, I would actually
Why
What does
is
that mean?
Titanic the same?
What's that?